Hey, here we go. So here's find the area of the region bounded by these graphs, okay? So first of all, if you graph these, are the individual graphs. And so when I first look at this, I would personally think, all right, in order to get a single region, I would partition the y-axis. That way, each of my little uh, rectangles would run this way, and I have a single function as the upper function and a single function as the lower function here. So you would need to find the intersection point, and that way that becomes your lower bound, and then this one becomes your upper bound, or 1. So we would use the y coordinates here, all right, because we're going to be partitioning in the y direction, all right. So you find the intersection by setting these two functions equal to each other, and it turns out you get a third-degree polynomial. And so you would have to use the Ruffini principle in order to get that, or I guess it would be, solving for third-degree polynomials, or since it's actually got an irrational root, I would actually then use my calculator. So you would graph these two functions, okay? Then you would do second calc, and you do intersect, which would be the 5. Then you have to hit the button 3 times. You have to choose your curves. So there's one curve, 3 minus 2x, so 3 minus 2x. And then the other curve is this one here, 1 over 1 plus x squared, okay? Click that one, and you find your intersection, and there it is, 1.317 and 0.365, and so forth. So there it is. So there's my point of intersection. All right. So now this becomes the lower bound for my area, and my upper bound is y coordinate 1. And then to figure out my area, it's this function, which would be this function solved for x, minus this function also solved for x, because remember, when it's a dy, when you're partitioning the y-axis, it's dy here, and you have to have y's in your thing, in your integrand. Then you look at this and you shoot, oh my, this looks like a bit of a tricky integral, right? So you're thinking, oh man, I don't know if I want to deal with that integral. So then you think, all right, well, maybe I'll partition the x-axis instead. But the issue with the x-axis is that you actually end up having 2 areas here. So let me draw on this here. So if I were to partition my x-axis, I would have one area here, this one, all right? And then the other area would be here, all right? And so this area has a lower bound. Now, if I'm partitioning the x-axis, it goes from 0 to 1. So that's 0 to 1. That's this area. And then the other one goes from 1 to 1.317, which would have been that the x coordinate of this intersection. So that goes from 1 to 1.317. Now, why is this turning out to be easier? You end up having 2 integrals, but this function here, its integral is arctangent. And so as a result, your integral becomes a bit bigger in terms of like more writing, but it's actually a very easy integral, because look at this, now if I just integrate these, so notice I've got my 2 areas, right, from 0 to 1, and then from 1 to 1.37. And remember, it's your upper function minus your lower function. So my upper function would be 1, and my lower function is this curve here. And then same with this, my upper function is 3 minus 2x, 3 minus 2x, which is this one, okay? And my lower function is this curve here, or 1 over 1 plus x squared. And there you have it. And there's my integral. Now if I kind of move over, now if I integrate this thing, I'm going to get, just this integral, the arctangent. And so each one of these 3 integrates to 3x, 2x integrates to this, and then I evaluate it from 0 to 1 and from 1 to thing. Remember, the arctangent of 1 is pi over 2, the arctangent of 0 is 0, and so forth. And you plug all this stuff in, and you apparently get somewhere around 2.95.